Okay, so we stopped at this slide in the previous video, and I'm going to continue down to this, which is basically a lab report. And I'm not going to spend time on these next couple slides because I have more detailed PVT data that I've provided, and I'm going to walk you through the calculations in that one instead. So this is just an example of what your flash data looks like. And again, flash vaporization is also known as constant mass expansion, CME, also known as CE, constant composition expansion. They're all the same thing. And the data is useful mostly only above bubble point pressure. Below bubble point pressure, we use data from the differential liberation, which is what you see on the next slide right here. So this is your differential liberation data, and we mostly focus on data below bubble point in the differential liberation data. And I'll talk more about that when we get to the calculations on how to extract the fluid properties of interest from PVT data. This is what your separator test looks like. It's basically gas-oil ratio and formation volume factor at different separator conditions. And we first figure out the optimum one and then pick up the RS at bubble point, which is solution gas-oil ratio at bubble point, and oil formation volume factor at bubble point. Those are the two most important parameters we grab from the separator test, and I'll be showing that shortly. So I'm going to skip these slides. They basically show you oil formation volume factor, gas-oil ratio, again oil formation volume factor, and gas-oil ratio using two different methods. But I'm going to walk through the calculations in these next couple of slides. So again, start out with flash vaporization, which is CCE or CME. This is the data we'll be working with from a standard PVT lab report. It shows pressure and something called relative oil volume. So what is relative oil volume? I'm going to spend some more time explaining this, but it's basically volume of oil in reservoir barrels at reservoir pressure divided by the volume of oil reservoir barrel at bubble point pressure. So that's what this relative volume is. And that's precisely what this is. It's VT over VB. And now you know what VT is, total volume at reservoir pressure. VB is reservoir barrels at bubble point. So it's a relative volume. The subscript F tells you is for flash, because you will later see other relative volumes which have subscripts D for differential liberation, and another one which has DB, differential liberation, and B for bubble point. So that alone tells you a lot about the different relative volumes we're going to be talking about. So we're not going to talk about this Y function. Of course, density is important. You will see how we calculate density above bubble point, and below bubble point we just grab density from the differential liberation data. So very important to know that when you are above bubble point, we will typically use data coming from flash vaporization. And when you are below bubble point, we typically will use data coming from differential liberation test. So some fluid properties are simply just read off from the lab reports, like bubble point pressure, which I showed earlier. And actually this is your bubble point pressure. Oil viscosity, there is a separate table that shows oil viscosity and gas viscosity. We'll talk about that shortly. So those we just read off from the data, and all the other gas properties we just read off from the data. The properties we need to calculate from these different lab reports include oil formation volume factor, and I'm going to be showing how we make these calculations, the solution gas oil ratio, the oil density above bubble point pressure requires calculation. Below bubble point pressure, we just read it off from the differential liberation data. Coefficient of isothermal compressibility above bubble point. We have an equation we'll use to calculate it, and because it is above bubble point, which data set do you think we'll be using? Flash or differential liberation? We'll be using flash, right? Because the flash is good above bubble point. Remember, the difference between the flash vaporization and the differential liberation is that in the flash, it's a constant mass expansion. So we don't take out any volume of fluid from the chamber. But in differential liberation, when gas comes out of the oil, as we reduce the pressure, we bleed out the gas, and we again expand it further and allow new gas to come out of the oil. And we keep doing that in multiple steps. And that mimics what we have in your reservoir. When you drop pressure with your well, you produce gas because the gas is very mobile, right? So the gas flows to the well and gets produced. And as the pressure continues to go down, gas continues to come out of solution and gets produced. So it's not a constant mass because we produce the gas. How are we doing on time?